In this video, I will define the continuous time Fourier transform, and then do a couple of key examples. First of all, don't be confused by the term transform. It's the convention to call the operations relating an input and output a function if the input and output are drawn from something like a number line, and transform if the input and output are functions. So a transform is just a function of functions. Let's set up a system for examination. We have an input, which is a function of time, and an output, which is a function of omega. Relating these two functions is the continuous time Fourier transform, defined as the integral from negative infinity to infinity of the input times e to the negative j omega t dt. X of t and capital X of omega both describe the exact same function, but with a different basis. This is why we label the input and output of the CTFT with the same variable. We just use upper and lower case of the variable to help distinguish them. The inverse continuous time Fourier transform looks similar. Capital X of omega goes in and lowercase x of t comes out. The operation is the integral of the input from negative infinity to infinity of the input times e to the positive j omega t d omega. The big attempt to give intuition and meaning to the continuous time Fourier transform is to say that you are moving from the time domain, where you decompose the signal into a series of points, to the frequency domain, where you decompose the signal into a collection of complex exponentials, which are, by definition, cyclical and infinitely long in the omega domain. In my opinion, there are so many different ways to understand the Fourier transform, and you will have so many aha moments while playing with it, that there's not much point to dwelling on intuitive reasoning. That said, I want to point out two things. If you multiply two functions together, the parts that are similar will get amplified, and the parts that are dissimilar will get diminished. And that when we integrate a function, we are summing the bounded area between that function and the line representing the domain. In the analysis of signals, we often plot the input and output of the CTFT. You should be familiar with how a time domain signal is plotted by now. The output of the time domain function is the input to the CTFT. The input to the CTFT can be real or complex, but we will generally be limiting the discussion to real inputs. If not specified, assume the input is real. Plotting the output of the CTFT is a bit more difficult. Generally speaking, the output of the CTFT is a complex function. This means we can either plot in 3 dimensions, which is difficult, or we can portray the output of the CTFT as 2 separate plots. We have a choice whether to use polar coordinates or split the signal into real and imaginary parts. As we proceed, recall the definition of the complex exponential. When we describe a complex exponential, z equals r to the e j omega in polar coordinates, we say that the absolute value of z is equal to r, and that the phase of z is equal to theta. When we describe a complex exponential in terms of its real and imaginary parts, we invoke Euler's formula, which states that r times e to the j theta is equal to r cosine of theta plus jr sine of theta, so that the real part of r e to the j theta is equal to r cosine of theta, and the imaginary part is equal to r sine of theta. For our first example, we'll take the delta function as our input. Plug it into the CTFT and simplify. We are left with the statement that x of omega equals 1 for all omega. In this particular case, we can actually draw this function in 3 dimensions fairly easily. If the function is viewed in polar coordinates, we see that the absolute value of capital X is 1 for all omega, and the phase is 0 for all omega. If we broke it up into real and imaginary parts, we see that the real part is equal to 1 for all omega, and the imaginary part is equal to 0 for all omega. Next, consider an input delta of t minus capital T. Plug the function into the CTFT and simplify. We are left with the statement that capital X of omega is equal to e to the negative j omega capital T. Now it's getting a bit more difficult to draw in 3 dimensions. The function repeats itself every time the angle of the complex exponential is equal to 2 pi times some integer. Since omega is our variable, we isolate it to realize that the function repeats itself every time omega is equal to 2 pi over capital T times some integer. Capital X of omega looks like a coil stretched out in the omega direction. In polar coordinates, we evaluate the magnitude of capital X of omega, which is 1 for all omega, and the phase, which we can just read off as negative omega capital T, and plot. For a Cartesian view, we consider the real and imaginary planes separately. For this, all you have to do is remember Euler's formula, which states that e to the j alpha equals cosine of alpha plus j sine of alpha. However, we have a negative sign in our exponent. Plug the negative sign into Euler's formula and simplify. The cosine of negative alpha is equal to the cosine of alpha, and the sine of negative alpha is equal to minus the sine of alpha. If those definitions aren't familiar to you, do some plots and examine the functions separately. For our last example, consider the input to the CTFT to be mu of t minus capital T. This is often referred to as a box or window function. Refer to the previous unit step video if you are unfamiliar with functions of this kind. When a box function is plugged into the CTFT, it changes the limits of integration from negative infinity to 0 to capital T. Use the fundamental theorem of calculus to evaluate the integral. Instead of simplifying the second term, e to the negative j omega 0, to 1, we're going to manipulate this equation into a useful formulation for analysis. To do this, we start with the popular trick of splitting the t in the first exponent into capital T over 2 plus capital T over 2, and the 0 in the second exponent into capital T over 2 minus capital T over 2. We then pull the term e to the negative j omega t over 2 outside the brackets because it is common to both. Multiply the negative inside the brackets. Then use Euler's formula to rewrite the terms inside the brackets as 2j sine omega capital T over 2. Finally, cancel the j term. The form we are left with is more or less what is known as the sinc function. However, the sinc function is defined differently by different people, so I'll try to avoid its use when I can. Let's rewrite the system now that we have a better handle on the output. X of t goes into the CTFT, and capital X of omega comes out. The two important formulations of X of omega are 1 over j omega times e to the j omega t over 2 minus e to the negative j omega t over 2 times e to the negative j omega t over 2, and 2 times sine of omega t over 2 over omega times e to the negative j omega t over 2. Our next task is to plot X of omega, and to do that we'll need some test points. Generally, when plotting by hand, we just look for the key points. Begin by evaluating X of omega when omega equals 0. To evaluate the function at omega equals 0, we must invoke L'Hopital's rule. The derivative of the numerator simplifies to capital T cosine of omega t over 2. And the derivative of the denominator is 1. So capital X of omega is equal to capital T when omega is equal to 0. Our first step was to find X of omega when omega equals 0. Our second step is to find when X of omega equals 0. X of omega is equal to 0 when e to the j omega t over 2 minus e to the negative j omega t over 2 is equal to 0. As always, refer back to the unit circle and the complex plane to gain intuition. The terms are equal, and so evaluate to 0 when omega t over 2 is equal to pi times some integer. Therefore, X of omega has 0 crossings at 2 pi over t times an integer. Already, I'm getting tired of plotting in 3 dimensions. Let's move over to polar coordinates. In polar coordinates, we can reason out the remaining plot from the points we already have. Consider the formulation that X of omega is equal to 2 times sine of omega t over 2 divided by omega times e to the negative j omega t over 2. The phase term can simply be read off as negative omega t over 2. For the magnitude, consider that the magnitude of the complex exponential is always 1, so it doesn't contribute. Another clue is that by definition magnitude is positive only. We are left with a sinusoid that decays at a rate of 1 over absolute value of omega, with this curious central lobe which resulted from our evaluation of omega equals 0. The points I've labeled are the only ones we really care about. If you are not convinced that this plot is correct, evaluate a number of the in-between points of x of omega by hand. We generally think of and plot the CTFT of box functions in polar coordinates. I'm just going to plot the general form of the function in Cartesian coordinates for completeness. I've never had to think of it in these terms.